Welcome to MEI Modelling with Algorithms. We're on the topic of algorithms, sorting, packing and complexity of algorithms, and we're on the final video of this topic, video 1.5, complexity of algorithms. So firstly, we're going to need to define a few important words that we're going to be using here. Firstly, the efficiency of an algorithm is essentially a measure of the run time. How long does it take to complete? And usually that just means the number of operations that are carried out. The size of a problem is a measure of the complexity of the problem. In the case of sorting algorithms, it's just how many items there are in the list. When we get onto the topic of graph theory, it's going to be the number of vertices. This then allows us to define the complexity, which is a measure of how the efficiency changes as a function of the size of the problem. And the order of the algorithm is also an indication of the complexity, and we'll define what we mean by the order on a later slide. So probably most of the algorithms that you will meet here will either be of quadratic order or cubic order. That will be written possibly using the shorthand notation, order n squared or order n cubed, where n is the size of the problem. And what that means is that the time it takes for the algorithm to complete will be proportional to the square, if it's quadratic, the square of the size of the problem, or if it's cubic, it will be proportional to the cube of the size of the problem. Why is this helpful? Well, what it means is that if we know the runtime for a smaller problem, then that will allow us to estimate how long it's going to take for a larger problem, and that will be the main type of question that we'll be dealing with in this topic. There are other types of order. There's exponential order, when the functions are n factorial, or 2 to the power of n. You might want to think about in practice why these might be more problematic. Essentially what it means is these things grow much more quickly than quadratic or cubic, and what it basically means is that there's going to be a much tighter limit in practice on the size of problem that we can deal with. So now we're going to look at how we might determine the order of the Quicksort algorithm, which we saw in the previous video. It's important to emphasize here that we're going to be dealing with a worst case scenario. In fact, the Quicksort algorithm is almost always better than what we're going to find here. So it's important to realize that we're just looking at a worst case scenario in this time. And just to keep things simple, all we're going to do to get a sense of the time this algorithm is going to take is just to count the number of comparisons that will be needed. So what is the worst case scenario in Quicksort? It's when the numbers are starting off in completely the wrong order. So if they start in descending order, then that actually gives us the worst case scenario, and it's going to take the most number of comparisons. Yeah, if we try to do Quicksort, then we're going to have to, the first time round, we'll pick 5 as our pivot, and therefore there's 4 other numbers that we're going to have to compare with the 5 in order to do that stage of the algorithm. So to start off with, we're going to have 4 comparisons. Once we've done that, 5's dealt with, we've got a list of 4 numbers, all of which went to the left of the 5. So 4 will be our next pivot, and there'll be 3 numbers that we'll compare with that 4. So that's another 3 comparisons. And of course that will just keep going, so we'll end up with 4 plus 3 plus 2 plus 1. So with a list of 5 numbers in descending order, Quicksort is going to require 10 comparisons. Now if we try to generalize this, so rather than the size of 5 we have a size of n, then the total number of comparisons is going to be, well, we can see here that we've started with, well, if we reverse this sum, we've got 1 plus 2 plus 3 and so on, up to, well, with the size of 5 we got up to 4, so that means we're going up to 1 less than n. So the final number in that sum is going to be n minus 1. And then if you know the formula for the sum of the first n natural numbers, what we find is that the total number of comparisons then is n minus 1 all over 2. Okay, now what's important here is not the details of that, but just how that thing tends to increase in size as n increases in size. So if we were to expand that bracket, we'd see that this is actually a quadratic expression. The leading term is a half n squared. And actually that half isn't particularly important either. The thing which is important as far as we're concerned here is the fact that it gives us an n squared. So as n gets larger, this thing grows in proportion to the square of n, approximately. So here's an example of this. Suppose it takes a computer 0.015 seconds to do a sorting algorithm of quadratic order on a list of 2,000 numbers. What we need to do is estimate the time it would take to do the same algorithm if the list was somewhat larger, 40,000 numbers. Now, we are told that this has got quadratic order. So what that means is that the time is going to be approximately proportional to the square of the size of the list. Now, there are various ways of approaching this kind of problem, but the easiest way by far is to decide how many times bigger the larger problem is than the smaller problem. Okay, so if we take the 40,000 and divide it by 2,000, like that, we can see that this is clearly 20 times larger. Okay, so if this is 20 times larger, the time is going to grow proportionally to the square of this, so we need to square that factor. So we're squaring that because we're dealing with the problem of quadratic order. And so what that tells us is because the list is 20 times longer, the time is going to be 400 times longer. So all we need to do now is take the original time, which was 0.015, that's how long it took for 20 numbers. We think it's now going to take 400 times as long as that, so I need to multiply 0.015 by 400, and that comes out as 6 seconds. So here's another example. The only difference this time is that rather than being quadratic order, we've got cubic order. So the size of the problem this time is given by this number 150. That's the smaller version of the problem, and that has taken 2 seconds. And we need to figure out how long it's going to take if it was a larger problem, size 2,000. So just like before, the first thing we're going to do is we're going to work out how many times bigger the larger problem is than the smaller problem. And doing that calculation, we find that it's about 13 times bigger, or 13.3 recurring to be precise. And because this is cubic order, what that means is that the larger problem is going to take this number cubed times as long to complete. So I now need to cube that, so let's do 13.3 recurring cubed, because it's cubic order, and that comes out as approximately 2,370. So 2,370 times longer. It originally took 2 seconds, so to get our final answer we need to take the original time, multiply it by this factor of 2,370, which is 4,740 seconds. So that concludes the topic of algorithms, sorting, packing, and complexity of algorithms.